Hi everyone, welcome to the second lecture in machine learning. So today we are going to learn an algorithm known as logistic regression, which is useful for classification problems. So let's see what this algorithm is about. So far in this machine learning course, particularly in lecture 1, we had considered a data set. So we had a data set D, which was a set of points xi and yi, where I goes from 1 to m, and each of the xi's was a k-dimensional real vector, and the yi's were scalar, right? So for this, in this particular case, we learned a functional mapping that maps xi's to yi's with some feature representation that takes in input xi and outputs a nonlinear representation, or perhaps a nonlinear representation of the input vector xi. Takes this and maps it to the corresponding yi's. So this kind of problem where the x is a real vector, and the yi's are real, is known as regression. That is, regression is basically mapping, learning a function that maps a real vector to some scalar, which is a continuous value. It maps it to a real scalar. So this kind of problem is known as regression. So today we are going to consider a specific class of problems known as classification. So in that particular case, in classification, each of the yi's are integers, where z is a set of integers. So today we are going to consider a special case where yi's are binary. That is, yi can have values 0 and 1. So the goal is to learn a functional mapping f, which is parameterized by some number parameter w, that takes in xi or some nonlinear representation of xi, and maps it to some discrete values, right? So there can be the y can be so there are the y can assume c different values, right? So f maps to y, maps x to y, so y can have c discrete values. So this kind of problem is known as classification problem, where the output is some discrete value, or you can say these discrete values represent some class. So perhaps 0 represent one class, and c represents the c plus 1th class. To give you an example, for example, if you have a particular image, let's suppose you want to classify a pixel. For example, you want to know whether this pixel belongs to an obstacle, or perhaps road, or perhaps to a traffic sign. Then basically you are mapping each of these, each of the pixels in the image to these particular classes, whether this pixel is an obstacle or a road or a traffic sign, basically, right? So we can consider such problems as classification problems. That is, we are classifying each of the inputs we are mapping them to some discrete values, or we are mapping them to particular classes where each of the discrete values represent a class basically. And today we are going to consider a special case, as I mentioned, that each of the yi's is a binary variable. So this kind of problem is known as binary classification. Binary classification. Right? That is, the function f maps the x to 0 and 1. Right? For example, this can be, to give an example, this can be basically, for example, you have an image, and let's suppose this image, you want to know whether there's a particular obstacle or not in this particular image, right? For example, one of the obstacle can be a car, right, or any vehicle basically. So you want to know whether this image contains a vehicle or not. So you can train your algorithm by passing many such images, the ones that have vehicle and the ones that have no vehicles, right? So you can input such images to a function. You can learn the function that takes these input images and maps it to some output value 0 and 1, where 0 represents vehicle and 1 represents no vehicle, right? So this is one instance of your binary classification problem. That there are only two classes, positive or negative, or like true or false, or like obstacle present or no, or it's not present. So this kind of problem is known as binary classification. So to take the discussion further, right? Sometimes rather than saying just yes or no, for example, if the function maps, for example, if our function maps x to just 0 or 1, right? We can take it further, right? We can consider that this function also outputs some degree of belief as to how much the function believes that x actually maps to 0, and how much the function believes that the x should map to 1, right? That is, we want to learn some degree of belief, or we want to have some quantitative values that not just tells, for example, we can learn the function that says 0 or 1, right? But this may not be a very informative functional mapping, right? Rather than just outputting the values, we can also force the function, or we can also like compute a function that also maps some quantitative values for each of these classes, which tells you some degree of, which gives you an idea about the degree of belief that this functional mapping thinks that the input belongs to a class of 0 or 1, right? So basically, in this particular case, we just don't want an output like yes or no kind of an output. For example, f yes or no. We just don't want these yes or no kind of answers, but we also want the function to take the noise in the data into account and output the probabilities of yes and no, right? So we want a function that says 0 or 1, but it also gives us some probabilities of the output y being 0 or 1. So in that particular case, we can have some degree of belief as to how much the function actually believes that the particular input data point belongs to class 0, or the particular input data point belongs to class 1. And in some often this can be very useful to give you an idea, to give you a real world example where this can be used actually. So let's suppose you are performing autonomous driving. You want to learn an autonomous driving policy pi. So we are denoting the policy by pi, which governs the behavior of your vehicle, of your autonomous vehicle on road. Right? So this policy governs the behavior of the vehicle on road, And let's suppose you're driving on an Indian road, right? A single lane Indian road, or perhaps a double lane Indian road, right? So this is your vehicle. We are noting by a square box. It's going in that direction. And let's suppose there's another vehicle coming from the, which is far away, coming from the opposite direction. And you want to know whether this vehicle is a car, a jeep, or an SUV. Or a truck. Right. Now this is very far off, right? And let's suppose, because in India, you know, like trucks usually don't give you side, right? Whereas SUVs like let you pass basically, right? So perhaps like your driving policy needs not just the output 0 or 1. So this policy will decide the behavior of this vehicle based on this SUV or truck, right? So the policy doesn't just need 0 or 1, but it also wants the probability that this vehicle is an SUV and the probability for the vehicle being a truck, right? So for example, then your behavior policy can take this decision into account, take the probabilities into account, and it can decide at the next cycle that actually again wants to evaluate whether this particular, it wants to compute again whether this particular vehicle is a truck or an SUV, so that it can decide its behavior, the behavior of the vehicle accordingly. For example, if it's a truck, perhaps you might want to move towards the left side, and if it's an SUV, perhaps you can just keep on going on the path, because the chances of the SUV coming on your lane is very low as compared to when it is a truck. Because in trucks, because the trucks in India, they have a tendency to occupy like 2 different lanes at, on a road, right? So perhaps this is an example where your degree of belief or that quantitative value that you assign to those classes which represent your degree of belief becomes important basically. So now we will see like how to learn such a functional mapping.